Hi, in this video I'm going to demonstrate the frequency response of the M Audio M-Track 2x2M. So what that means is that I'm going to inject a signal. I'm going to start with a sine wave. I'm going to start from 20 Hertz and sweep right across to 20 kilohertz. And I'm going to measure how the M Audio M-Track responds. And how I'm going to do that is I'm going to use kind of an old software called Cool Edit Pro. And I'm going to record the input that comes into the computer. So this is kind of a quantitative test on the frequency response. So what I'll do is I will then record the input. For example, let's increase the amplitude. So there you can see I'm going to record the amplitude, the output of the M Audio. And I'm going to see what the total envelope looks like, and you can hear it in the background there because it's I'm putting in a sine wave. So what you will be seeing is me inputting a signal from this device here. This is called a function generator, and it generates frequencies. So as you can see, I'll be selecting, there's 100 Hertz, kilohertz, 10 kilohertz, and this obviously goes quite high. But obviously the audio spectrum for human ears is only up to 20 kilohertz, although there is some publications on the frequency range extending higher than that, because there was a publication saying that people could hear the harmonics by saying the audio sounded better, even though human ear can only hear up to 20 kilohertz. But when the harmonics of, say, a cymbal reach above 60 kilohertz, people were still able to experience that. So anyway, that gets into the psychoacoustics, which I'm not getting into. What I'm going to get into here is the audio response, the audio response of the M-Track 2x2. So I'm literally just going to inject a signal, sweep through, and see if the amplitude of the signal remains stable. So that I want to see if the M Audio is going to be attenuating that, or maybe amplifying it, and does it add any distortion. So this is a good experiment to test how accurate the M Audio's ability to convert analog signal to digital, how accurate it is in doing that task. So what is happening here? This is where I'm injecting the signal. So this would be your guitar or your drum kit, maybe just a microphone. Whatever it is, this is where your input is. Maybe it says instrument. If you're coming in the back here, maybe there you're using the, for your microphones or whatever. So you could do the same experiment on the back. I'm just using the front because it's got a jack and it's easy for me to get access to. Now what this is a device called an oscilloscope. An oscilloscope is a piece of test and measurement equipment which allows you to observe waveforms. So you can see there it says 117 millivolts at 299 Hertz. So as I vary the amplitude, you can see how it's showing me 163 millivolts and how on the display here it increased. And if I increase the frequency, as you can see, it's increasing over there. And that's what you saw me do on the computer, how it made more sine waves as I increase the frequency. So for those of you who are not sure what this is, audio sounds that are low, like in the 100 Hertz range, tend to be more the bass, the very low end bass. And as you go up the frequency range, 1 kilohertz, that's kind of getting to your mid range. And then 10 kilohertz, this is getting quite high. This is your treble, and upper treble will be your 15 kilohertz. And you can listen to these signals on your headphones, and you can get an idea of what these sounds are like. You can see now I'm at, let's put this at 10 kilohertz. There we go, 11 kilohertz. It's getting quite high pitched. And above about 15 kilohertz, most people over the age of 40 can't hear much above 15 kilohertz. A newborn baby could hear people even say a newborn baby can hear 22 kilohertz, up to 22 kilohertz. But for most people over the age of 40, they've lost a lot of that high end range. But that's not the point. The point is can the audio interface still deal with these frequencies? Because they still add to the experience of sound. So what I'm going to do now is I'm going to sweep through the frequencies and observe how this M audio responds. Okay, here we go. Right, I've just started the recording. I'm going to set the amplitude now. I've set the amplitude at 680 millivolts. And now what I'm going to do is I'm going to sweep across the frequency range starting at just under 10 hertz. Okay, I'm now at 260 hertz. I'm now approaching 2 kilohertz. Right, now I'm going to go test it from 2 kilohertz. Going up, there's 5. And this is where the most important part comes in, and that is the high frequency, for the reason that this is when the A to D is at its busiest. Okay, there we go. We're now just hitting 20 kilohertz about now. There we go. Okay, so we are about 20 kilohertz. And it's now gone to 677. So the output of the function gen did shift a tiny bit. So I'll take that into consideration. And we'll have a look at the signal on the screen shortly. But I just want to show you what I'm doing here. Right, so you've seen me injecting the signals into the M Audio M track. I've been playing with the function generator, but you haven't seen the output waveform. So now I'm going to move to the output waveform and show you the screen grabs of this. Well, I'm actually going to show it to you real time. So I'm going to kind of be redoing the test. I'm just going to talk you through what I'm doing. Now, the first thing I'm going to do is I'm just going to calibrate the signal. Now, what I've done is I've set it at 1 kilohertz. And as you can see that at 1 kilohertz, the amplitude is at 0.55. Now, what is this on the right hand side? This happens to be a scale. It's on nominal. Think of this as the volume. It could be dBs, it could be voltage, whatever you want. I've just set it to a nominal scale, and there it says 0.55. So that is my reference value. So ideally, as we adjust the frequency and sweep through the frequency range, this should stay at 0.55. Now, I'm going to now set the function generator to a much lower range. Remember, we are going to be testing this M Audio M track frequency response from almost 0 hertz, well, like maybe 5 hertz, all the way up to 20 kilohertz, and there I will go beyond 20 kilohertz and show you the response above 20 kilohertz. So I'm going to have to do this in stages because I can't sweep from 0 all the way to 20 kilohertz. My function generator doesn't give me that range. I have to go from in batches of 2. So I can go from 0 to 20, 20 to 2 kilohertz, 2 kilohertz to 20 kilohertz. So I'm going to do my best, but I'm just going to show you the first part, which is the low frequency response. So I'm going to start a new sample here, and you can see this is a new waveform. You can see the sample rate is 192 kilohertz. So that is the sample rate that I'm sampling the inputted wave from the M Audio. Now, obviously, you'll still also have to take into consideration the settings you've done on the sound side here and what frequency options you've chosen there, because obviously that also is important. You must set everything to the highest. You want the M Audio to operate at its best possible levels. Okay, so I've started the function generator. It's at almost 0. Call that half a hertz, and now there we go. I'm increasing it, and let's have a look at this amplitude or the roll up as it starts. There we go. I'm now at 8 hertz, 9, 10. I'm now approaching 30 hertz. So that's 30 hertz. So this is the beginning or the very low frequency response. Now, as I said, I'm going to pause the waveform because I now need to change the settings here on my function generator, because I'm now going to sweep right through from the low frequency and go all the way through to 20 kilohertz. Here we go. Right, I'm now at 55, and I'm going to sweep. There we go. I'm now at 300 hertz. I'm now at 1 kilohertz. And now I'm at 3 kilohertz, 4, 5, 7, 10, sweeping very quickly 12, and now it's when it gets important. This is when your A to D is really pumping. It's at 16 kilohertz, and this is the most interesting part. What is this M audio going to do above 16 kilohertz? Is it going to attenuate the signal? I'm at 17 kilohertz about, tell you when, now. That's 17 kilohertz. And now let's take it to 18 kilohertz. There we go. I'm now at 18 kilohertz. And okay, so I'm at 18.5 kilohertz. And if we analyze this quickly, you can see how as I increase the frequency from about 30 hertz all the way up to 18.5 kilohertz, it's a fairly good response. If you look at it, look, there is the calibration point at 0.55. This is very good. I got absolutely no complaints across this frequency range. As you can see, I'm scrolling through here, the sweep. There was a bit of drift there. That could have been some offset. I'm not going to be go focus on that drift. I'm going to go back here and say, look at this. Even in the low frequencies, it's pretty stable. This is a very good response. But now we come to the critical area. What is it going to do at its upper frequency cutoff point? And this is the important point. Now what I'm going to do is I'm just going to reset my function generator, because now I have to step it into the next range. So now I'm just calibrating my function generator to 18 kilohertz, getting ready to go between 18 and a half and maybe 25. Right, let's record. Whoops. That's unfortunate. Okay, so there we go. I'm continuing. I'm at 18, just over 18 kilohertz. There we go. I'm going to go slowly here. I'm now at 19.5 kilohertz. 20, sorry, it went too fast. Let's go back. I'm at 18.9, still within calibration. I'm now at 19.7, still fine. I'm now at I'm at 21 kilohertz. What I do notice is when you change the kilohertz, so for example, that's 20, it's now lower than the calibration point, so it's obviously on its minus 3 dB roll off. But I'll just show you something. If I reduce the kilohertz, can you see how going from 20 to 17, there was quite a change in the amplitude. And if I go from, say, 16 to 18, no problem. And now I'm at 19, 20, there we go. It is definitely rolling off. You can see the amplitude is rolling off. I'm now at 22 kilohertz, 21.6 there's rolled back a bit. So you can see there, just above 20 kilohertz, the attenuation becomes quite excessive. It's obviously set that way. They designed it like that. So at 21.5 kilohertz, this is what you're getting, a very reduced amplitude. This is where we were. And if I go back a tiny bit, let's go to 20. Let's see if I can take it to 20 on the dot. That is 19.9 kilohertz. And let's go to 20.5. That's 20.5 kilohertz. So as you go over 20 kilohertz, the M audio, M track is rolling off. Rolling off means it's going to attenuate any frequencies above that. And if you're interested, let's just take it up to 25 kilohertz and see what it looks like. This is 24.8 kilohertz. Look at that, 0. So the device is set to cut off any frequencies above a certain amount. Can you see it doesn't actually attenuate them, it just cuts them off. And when I say it doesn't attenuate them, is attenuate usually means kind of reduce. If I go back a little bit, there we go, I'm now back to 21. You can see that if I go to 19, there is the pass band, is no problem. And as I increase it's moving to its cutoff point, it's attenuating. There we go, it's attenuating. But why I say it's cutting off, I mean like it's disconnecting. Look at this. Because if I go to 21, major attenuation there. And if I go to 22, major attenuation. And if I go to 23, boom, disconnect or cut off. What I mean is it almost cuts off the signal. So there we go. That is the frequency range of the M audio. Now, if you're wondering what does this tell you? It tells you that if you've got frequencies above 20 hertz, 20 kilohertz, they're going to be cut off. That is fair. There's nothing wrong with that. That is how it's supposed to be in terms of digital audio, because they base it on the rule that our ears cannot hear above 20 kilohertz. Although that is not necessarily a truth. There have been studies done that prove people can experience music above 20 kilohertz. And that is why the very high-end audio equipment can play well over 30 kilohertz still with a flat pass band. Okay, so that is the response. Now, you might be interested in what it looks like if you shove a square wave in. And you might be wondering, why on earth would you shove a square wave in? Well, I tell you what, looking at the response of a square wave tells us quite a lot about how the sound card handles harmonics. Now, I'm just going to calibrate it at 1 kilohertz. That is just above 1 kilohertz. So what you're looking at is a 1.041 sine wave, and I'm going to turn it into a square wave. So I've now just set the function generator into square mode, and this is what a 1 kilohertz or 1.04 kilohertz looks like in the M audio. For those who know about audio, you'll see that we have quite a lot of ringing here. It still looks like a square. Ideally, if it was a square, that would be amazing, but it won't be because of the reason that it cannot handle all the harmonics. You see, to make a square wave, we need an infinite amount of sine waves. And obviously that would mean the frequency range of the unit would have to be very, very high in order to get that response. Now, I'll just show you one more time. Let's go a little bit closer here. I've just adjusted. I noticed there was some offset there, and I've just corrected for that. Right, so let's see where we are now. Okay, so this is a 50% duty cycle square wave being fed into the M audio. And that's what it looks like. That's a square wave. There you see 50% and still has the ringing. It's not terrible. If you look at it and what it looks like on the scope, it looks like a square wave. A square wave means straight up 90 degrees, flat top, drops 90 degrees. So it's a vertical line, horizontal, vertical. You can see there is a little bit of a angle there. It's got a lot of ringing. Okay, so that's what the response of the M audio is. Overall, it's a fairly good response. I also noticed, if you are interested, it didn't make much difference when I changed these settings. Actually, it didn't make any difference. So I'm not sure, maybe people from M audio could explain. I did set Cool Edit Pro to the highest levels, and it didn't make a difference. It seems like this is more to match to whatever software you're using. So if you're going to set your software to 192 kilohertz, then try and set the M audio to 192 kilohertz, something like that. But in terms of the quality, it doesn't mean necessarily you're going to get a better signal from what I've just demonstrated here. All right, so that brings me to the end of the video. Thanks for watching. This was the frequency response from 20 to 20 kilohertz on the M audio. Overall, I say it's good. I didn't have a problem with it. Thanks for watching. Cheers.